Okay, I guess I should start. Johan is here. Should I start? Oh, okay. Regarding the morning talks about the stellar dynamics, some time ago, I heard from Martin Rees that stellar dynamics is hopelessly beautiful, and then comes the gas, takes away the beauty, and also the hopelessness. Okay, so I more or less know what I'm going to talk in my remaining talks. Today's talk number 2. I will talk about the angular momentum problem, mergers. On Thursday, I will talk about mergers and cold accretion. And then in the last day, I will talk about the central kiloparsec and maybe origin of the supermassive black holes and the effect on the evolution of the galaxy. Now, let's get somewhat serious. There are, when we talk about angular momentum, there are two prospective conservation laws. One is the total angular momentum of dark matter and baryons, and the second one is the distribution of the angular momentum, say, with the mass. Now, the angular momentum, which is described here, denoted as J, can be expressed in normalized units, which first goes to Peebles, 1969, and that's the lambda parameter. Here it is. So it depends on the angular momentum, total angular momentum of the dark matter and baryons, the energy, the Planck energy of the system, the gravitational constant, and the mass of the system. However, it is a little bit complex definition. And over the years, alternative has been proposed, which goes to still the total angular momentum remains, the mass, the virial mass of the halo remains as well, the size of the halo, the virial radius remains, and V, which is the circular velocity, which is measuring the virial temperature of the halo. Now, numerical simulations show that this dimensionless parameter, spin, is this numerical value is around 0.033 to 5%. And if you want to know the difference between the Peebles definition and the later definition of lambda, which I here describe as lambda prime, but I will sometimes forget to write this prime, the difference is simply depending on the ratio of the singular energy of the singular isothermal sphere in units of the NFW. So I mostly will be using lambda prime. As I said, it will be usually without prime. So the other thing that I would like to introduce is something that is puzzlingly interesting, especially the late time, this log normal distribution. It is as interesting as Gaussian, and it is not very much different, but it has this ln here, so that's why it's called log normal distribution. So the numerical simulations of pure dark matter halos show that their distribution with the spin closely follows the log normal distribution. And that is independent of redshift. And the average value is about, the average value is around 0.035 with some dispersion around this. Overall, the lambda, the spin of the dark matter halos, is the range of the spin is between 1% to 10%. Now, if we define specific angular momentum, which is just the total angular momentum normalized by the total mass, one can hope that the disk size distribution is directly related to the distribution of the halo spin. So I first brought up a simple analytical example. The analytical examples are usually indispensable. If you take an isolated sphere, uniform sphere of gas rotating, and if it is collapsing to a disk, and if we somehow get exponential disk, then without dark matter, then the spin of this disk will be about 0.425. That's possible to calculate simply analytically. So what I would like to know now, if I start with a particular spin, where will I end? What size of the disk will I get? And this is isolated disk. So here is the initial spin in the units that I define: specific angular momentum, the virial radius of the halo, and the virial velocity, or circular velocity, describing the halo. So this is the initial one, and this is the final one. So I take the ratio of initial in units of the final one, and I just divide the expressions. And I assume, for simplicity, that I'm talking about isothermal sphere, so the virial velocity is independent, circular velocity is independent of radius. I get that the ratio depends on the ratio, square root of the ratio of the radii. This is really bad. It is bad for simple reason that in order to increase the spin and get rotational support in the baryons, one needs to if you want to increase the spin by factor of 10 in order to get the rotational support, you need to collapse by factor of 100. This only happens in the universe which doesn't have these galaxies. So that's why I wrote very bad. And if you do the same estimate within isothermal dark matter halo, you get that the ratio depends not on the square root, but just on the linear ratio of this radii, which means in order to get rotational support, the gas needs to, or baryons needs to collapse only by factor of 10. This is, by the way, a very interesting and independent proof of existence of dark matter halos. Okay, let's see if we take and really do a serious calculation with coefficients and then invert the spin and this ratio in favor of the size of the disk. This is what we get as a function of redshift, where V is just the circular velocity. So the only dependence here is the dependence on the Hubble constant. Okay? So I bring up an example, the Milky Way halo, which has a size of 120 kiloparsecs. Disk optical scaling is 4 kiloparsecs. So it's not bad at all. But there is an interesting consequence to this relation. And that is that galaxies or baryons that start in the halos with larger spin will have larger size, and so they will form disks of lower surface brightness. So the conclusion that I want to make in from what I discussed so far is that if the baryons collapse within dark matter halos and the angular momentum, the specific angular momentum, is conserved, then all what is needed, a collapse by factor of 10. And this is in rough agreement with observations. Now let's see what observations tell us. This is a distribution of disk sizes versus the maximum of the rotational velocity, which measures the mass distribution, from Cortot 1997 sample of local galaxies. And what you see here, that the lambda prime, the deduced spin of the dark matter halos, is around 0.025. The theoretical value is around 0.035, so the difference is not so bad and means that as in real universe, the baryons don't lose all of their angular momentum as they collapse. What about the higher redshifts? Well, of course, there are all these problems that observers face and never theorists. What we have here, a sample at redshift 2, and we have the disk half-light radii versus the same maximal circular velocity of these guys. The triangles, the empty triangles, are the dispersion-supported galaxies with approximately 40 to 80 kilometers per second dispersion velocities, while here we have galaxies which are supported mainly by rotation, like Milky Way. And the lines that we have here, the dashed lines, are the theoretically calculated lines of constant lambda prime, constant spin. And so you see, the correspondence is really not bad. You increase the rotational support, and you get larger guys, as the theory predicts. So one should be encouraged by these results. Now, what does it tell us? Should we expect any problems with spin of baryons that collapse inside dark matter halos? No, it looks very nice, and that's why what comes later is quite unexpected. Here is what observations tell us about these galaxies. We have large disks rotating inside large halos. This is what simulations tell us. You have small guys, maybe by a factor of 10, smaller than on the left. I didn't measure this. This is what one would call angular momentum catastrophe. There is a clear disagreement between observations and simulations. Possible to turn down the light a little bit? No reaction? Okay. So let's check again this angular momentum catastrophe. Now, theory versus observations versus numerical simulations. What we have here is a specific angular momentum of the disk versus the log of rotational velocity. The simulations are here. The theoretical predictions that baryons collapse with the constant specific angular momentum is this line. And the observations are squeezed between this and this. And it's kind of an average with lambda prime 0.035. Again, the discrepancy between so-called theory and observations is not so bad. Well, maybe baryons lose a factor of 2 or less of their rotational support, of their specific angular momentum. But it's clearly contradicted by numerical simulations. Okay, Tully-Fisher relation in the infrared. Again, these are the same simulations. No, I mean the same data, not the same simulations. Simulations are better. So we have here I mean better than they've been before. I mean not better than not better than observations. Okay. Okay. So we have here the luminosity, infrared luminosity in I band versus the circular velocity. Please pay attention only to these full large circles. These are the simulations. These are also simulations, but they're bad. So we ignore them. So what you see here is that overall correspondence in the slope is not bad at all. But there is a shift, right? And what does it mean? It means that for specific luminosity, the disks rotate too fast. Why do they rotate too fast in numerical simulations? Because they are too compact. Okay? So the problem stays. I mean the angular momentum catastrophe. How can we resolve it? The beautiful thing is that we don't know how to resolve it. So there is work for all of us for years to come, at least for theorists. However, there are conspiracy theories, and I will mention 4 of them. First, the rotation curves. The idea was that numerical simulations are simply wrong because they don't have sufficient resolution. And indeed, nobody is against increasing the resolution. You see what happens, however. Increasing the resolution, 2 things happen. The maximal rotational velocity goes down, here and here, and the whole profile of the rotational velocity goes down. Okay, so one would think that this is in the right direction. Unfortunately, it is moving in the right direction, but insufficiently. So that's where my conclusion comes. The resolution has an effect on the central and outer regions of the simulated galaxies, but not sufficient. And what to do? What is the medicine? Well, of course, increase the resolution. In this particular case, the SPH codes. Okay. The second conspiracy theory is that, well, maybe the angular momentum is not conserved because of numerical reasons, and one can specifically focus on particular reasons. Cosmological numerical simulations miss the central to resolve the central parts of galaxies. Cosmologists discovered that there are bars only a few years ago, so it's only natural. And there is also excessive interaction between the outer parts of the disk with the dark matter halo and transfer of angular momentum there. And what you see here is low-resolution simulations. You see the end product after 5 gigayears, and these are just baryons with 30,000 particles. You see the disk is miserably small. It is slightly bigger and better, but still looks ugly when you go to 100,000 particles. And when you go another factor of 10, then it starts to look more decently. Okay? So one would say, okay, you need to increase the resolution, but also maybe a better treatment of interstellar medium. Now comes the third conspiracy, and that is that in numerical simulations, and that reflects our physical knowledge, of course, one-to-one, the baryons can cool down quite easily. And as they cool down, here is the dispersion velocity, which Alatumre invented about, 45 years ago. And out of this relationship, one can immediately define the infamous Q parameter, which leads to star formation, say, when the Q is less than 1, or simply fragmentation. Here the numerical simulations of that is the gas. This is just let the gas cool down. You see, you get few clumps. If you use isothermal equation of state, it is slightly better, but not sufficiently. And only if you introduce multi-phase interstellar medium, it starts to look like a gaseous disk. In order to do this, here is the equation of state that was used by these simulations. And this is the pressure versus number density in the gas. And it has a threshold for star formation at 0.1 particle per cubic centimeter. So it's isothermal equation of state here. And as we cross the threshold for star formation, we introduce additional hot phase. That was done first by Springel and Hörnquist in 2003. And you see that the pressure goes up dramatically more than in isothermal case. And that's why the gas is prevented from collapsing. So clearly we need a multi-phase model for the ISM. Unfortunately, this multi-phase model that we have today increases the pressure in the gas above the cold phase, but it doesn't allow the cold phase to be dynamically independent from the phase, the cold phase from the hot phase, and therefore this is really not, in a way, not a self-consistent problem. Okay, the last conspiracy is that both baryons and dark matter like to clump, gravity to blame, of course. As the dark matter clumps, it can entrain baryons. These clumps, dark matter clumps, will experience dynamical friction, and we will talk about this later, and collapse to the center. And of course, the angular momentum will go away. As a result, you will have over-concentration of stuff in the center. I mean, very cuspy distribution. So, how to deal with this? Well, there clearly was claimed that there is excessive substructure in the dark matter. But this is not clear. And in fact, every of these conspiracy theories can be inverted from being numerical problems into our misunderstanding of the basic physics. We have no idea why this happens, although some people are very optimistic. Okay, so my point is that simply that excessive substructure may actually be needed in order to solve the problem of the Caspi NFW profiles. Maybe not, but it's not clear that one should immediately eliminate it. So you recognize who is this, right? This is, okay. So we don't understand, we don't even know how to formulate the problem, and there are rumors that maybe feedback will help. Then the question is, what feedback? And I will try to, if I will get to this on Thursday, try to address this problem. Okay, so far we've been talking about angular momentum catastrophe, so the amount of angular momentum. Now the distribution of angular momentum. Already in the 70s, I think the first person was Ken Freeman, well, maybe Mester, actually, who suggested that, or tried to explain why the galactic disks are exponential. That was Freeman. And the idea was, what if we start with the uniform gas sphere in the solid body rotation, then we can naturally, conserving angular momentum in baryons, get exponential disks. The answer today to this is the idea is okay, But this is not, the initial conditions are not uniform gas sphere in the solid body rotation, although the difference is not so large. Okay, so what is the distribution of the angular momentum in the halo which leads to more or less exponential disks, assuming the angular momentum is conserved? Well, with a little bit of algebra and numerical simulations, one can come up, this is the distribution of the probability distribution with respect to specific angular momentum. Now, there are assumptions here. First, all the angular momentum, all the particles, all the matter should go in one direction. So no counter-rotation here. And you also assume that all the angular momentum is correlated, which means all the baryons have the same direction, the same z-axis. Okay. Then one can actually write this two-parameter family, which depends on J0 and mu. And for 90% of the dark matter halos, mu has a very narrow range between 1.06 and 2.0, with the average of 1.25. So it is not difficult to convert the probability distribution into distribution of mass with angular momentum. And you get this when the m is the virial mass of the halo, and mu and J0 are the same guys that I defined in the previous transparency. So one can plot the m as a function of, for all the mass which has specific angular momentum less than some j, as a function of j over the maximal angular momentum in the object. And you get more or less similar distributions, and the difference here is only different mu. Mu is decreasing from right to left. You see this dashed line? This is the uniform sphere solid, which rotates as a solid body. So the difference is not so large. You can superpose these curves and get this universal angular momentum distribution. Now, does it lead us to the exponential disks? Because that was the motivation. I prepared this formalism, but definitely will not use it. But here is the result. Here is the surface density of the disk as a function of radius and the parameter mu. You see that it is not exponential. But, you know, there are many functions in mass which are quite similar to exponential. So let's take a look. Only the upper left corner. If you do a more careful calculation from conserving the angular momentum of baryons, then you actually arrive to distribution which is given here by this thick line. Don't pay attention to this cutoff, because that's just because the system has a finite radius, so it's artificial. The exponential disk is here, this thin solid line. So what do you see here? You see that there is a problem. The problem is at small radii, clearly there is too many baryons at low angular momentum, low radii, sorry, and there are too many baryons at large radii. Okay, which means, in fact, there is overabundance of baryons at with small angular momentum and with large angular momentum. A few years ago, a sample of 14 dwarf disk galaxies been observed in order to compare both the spins of their halos, I mean a little bit modeling on top of observations, and the distribution of angular momentum. So what you see here is, this is the log normal distribution that I discussed a few minutes ago, and said that basically there is no dependence on redshift. And these are the observations, okay, the dashed line. So the difference, so this is the distribution of lambda. So this is the distribution of the spins of the dark matter. The difference between baryons, which are the galaxies, of course, and the dark matter is not large, so one can say we're happy with this. Here on the right, you have now the distribution of angular momentum, which I just call angular momentum distribution, as a function of angular momentum. And you see that the halos, or pre-collapsed baryons, have this line, while the disks, which are these dwarf galaxies, have this line. Quite a different distribution. So the angular momentum distributions of disks has been concluded as being quite different from that of dark matter halos. But their spin distributions are more or less similar. This is basically going over all these galaxies, 14 galaxies. I don't think I have time for this, so let me skip and go here and to make few conclusions. Here we have again this main point. Here is the disk angular momentum distribution, which is the post-collapse baryons, and the pre-collapse, the dark matter distribution. And you see the colored regions, that's where the discrepancy is. Okay? There are many issues which follow from this, and one of them is that apparently the fraction of baryons that end up in the disks is much smaller than the universal fraction of baryons in the universe. And so the $100 question, as we say, is how can this small fraction of the baryons take all the angular momentum? So the grand conclusion is the angular momentum distributions in dark matter halos do not correspond to the observed one, even if angular momentum is conserved. And so either there was some angular momentum redistribution among the baryons as they collapse, or the decoupling between the baryons and dark matter happened before they started to move into the halos. And there are some ideas about this, but there is no resolution. Just to say a couple more words, there was a recent paper, just maybe a few weeks ago, by Fisher and Rory, and the previous paper by John Corman did on the same issue. And that's where it's a survey of bulges inside a sphere of 11 megaparsecs, centered on the Milky Way. And what you see here, that 80% of galaxies within this mass range have either pseudo-bulge, although I don't like this definition, disky bulge may be better, or no bulge at all. And then the classical bulges and ellipticals are responsible for 1/4 of stellar mass within this sphere, and the spirals for 3/4 of this. But the main problem is, of course, how to avoid classical bulges, how to avoid these large bulges which are given here. No, I didn't. Yeah, here it is. Bulge over total mass. This is smaller than 0.2. I mean, more than 0.5. How to avoid them? Apparently, most of the galaxies don't have it. Now, recent work by Phil Hopkins, actually mentioned or claimed that the pseudobulges are formed from mergers. That would make the problem intractable, because we do more or less know what is the rate of mergers, but we don't see their products, and that's large B over T's. So is this another catastrophe? I just summarized the current paradigm, and that is small bulges are maybe results of the internal secular evolution of galaxies and related to disk properties without merger activity. But if this is true, then too many galaxies are observed without bulges. And need a main revision of merger rates, maybe. Okay, what is the origin of this universal angular momentum distribution? Well, the idea in the 50s, 60s, and 70s was that this is the result of the gravitational torques. But there are two opinions. One is that the angular momentum is acquired in spherical shells as the galaxies, proto-galaxies, still expand, and very little comes later in nonlinear stage. The other alternative is the angular momentum is acquired in mergers, and the initial angular momentum is not so important. I am not going over the TTT or triple T theory, but the essence of this is very clear from what I said until now. So I skip it and ask myself a question. What is the response of the system to mergers with respect to the angular momentum? Here is there are two independent groups. Here is the spin, the halo spin, as a function of time in gigayears, and major mergers in the middle. And you see that indeed during the merger, angular momentum is increasing dramatically, but then apparently because of the internal redistribution of this angular momentum, it goes away. So this is in complete contradiction with the idea that major mergers supply angular momentum in every single event. And we actually know where is the problem. I mean, here is the same group, and this is the definition of spin, the halo spin. And you see that in the merger, the angular momentum goes up, then declines. But what really kills it is that the mass of the system, which is given by this line, the mass to the power of 5, it's 1 over m to the power of 5 halves, is declining as well, which means that the mass is dramatically increasing in the merger event. And so the net response is here. So from high-resolution dark matter simulations, there is no steady increase of the spin of the system with time. So some summary. The angular momentum catastrophe, hydro simulations show that the angular momentum of baryons is not conserved during the collapse. We don't understand why. And all the solutions proposed so far are more like a fine-tuning. And then there is the angular momentum profile mismatch, that the distributions are quite different. Okay, we go to the disk grows. Okay? Now, what is the ideal system? If we think that logic is the base of science, and we live in the universe that has gravity, we have a system that has some rotation that is collapsing. What is the ultimate limit of such a system, evolutionary limit? Well, it's very simple. You have all the mass in the central supermassive black hole, and the negligible amount of material is going to infinity, but takes all the angular momentum. Okay? If you know physics, you need to arrive to this limit. Nature doesn't follow this limit. And that's kind of troublesome, right? And the understanding why it happens is that one of the main problems in physics is the angular momentum redistribution in systems. And the efficiency is maybe very low. I was told that this was done actually here, somewhere in the island. So if anybody recognizes where it is, it would be interesting. A few years ago, Stirling Colgate published this paper. Angular momentum is the cosmic pollutant. Well, this is his weak point, actually. He is capable of discussing the problem of angular momentum redistribution at any time of the day, in any state of mind that he is. So you actually Google and read it. It's very entertaining. Disks can form either slowly, adiabatically, and this would be linking them, their memory to initial conditions, or fast, and that would be a dynamical process, so they will forget the initial conditions. Disk secular evolution. That's the main subject of this conference. What affects the disk growth? Well, there are two things. Environment, not two, four, I counted. Okay. Environment, it depends where the object sits, in the field or in the cluster. And here I compiled a list of particular processes. In the cluster, we have high dispersion velocity, so we have what is called galactic harassment, interactions, but little mergers. In the field, we have low dispersion velocities, and so we have little harassment, but a lot of mergers. And then there are other things like tidal interactions, RAM, pressure ablation, strangulation, and so on. The second thing is the rate of star formation and feedback. That would definitely affect the system. How much mass the system is capable in losing in collective efforts by generating galactic fields. Galactic winds, of course. Then local and global dynamical instabilities. The list is quite long. And then, of course, what affects the evolution in our universe are the numerical effects. I find it inspirational. All the data, all the results, all the causal connections are here. And you, of course, recognize this picture. And here's the X-ray version of it. Okay, now what do I want to talk about in the half hour that I have? Well, of course, the main point, how did this grow? Mergers, smooth and clumpy accretion, and filaments. I will only touch mergers today. And so when I talk about mergers, I would like to define the criterion for merging, demographics of mergers, then relationship between different mergers. I will not get to Starburn AGN, probably even the whole week, if I would talk all the week. Minor mergers I also will skip. Transformation of galaxies in clusters, harassment, cannibalism, RAM stripping, triangulation, maybe. So, galaxy mergers. It presumes that stars and cold gas already exist, and interactions and mergers somehow should depend on redshift. There are quite wild assumptions here, so I prefer to put question marks here. Mergers, definitely, I mean, whatever I put there, I mean, it's positive, okay? Not a negative power. So mergers dominated in the past, and apparently the future that we are up to will be quiescent. On the other hand, we have as an alternative, the cold gas accretion. It may be smooth, clumpy, may come in filaments, and it is clearly decreasing with time. Both options, left and right, depend very strongly on the environment, and I already mentioned clusters where the merger process and maybe gas accretion are really quenched. Why do we need to study mergers? That's always the question that I'm asked. Well, because we need to prevent this, right? We are on the collision course with Andromeda, and here are the details of this famous collision. The distance is only 700 kiloparsecs. The line of sight velocity is minus 140 kilometers per second, and the approach time is, 2 gigayears, and the tangential velocity is, of course, not known, but soon maybe will be known from Gaia. Now, I stop here talking about this simply because I really think that, or I was taught that astronomy is about the past and not about the future. Okay, so we go further. So I would like to talk now about criteria for merging and then merging demographics. What happens in merging process? You have one galaxy interacting with another galaxy. I mean, so you have two, and you get only one. That's what is called merger. And the example probably is depicted here below. Mergers are beautiful. They inspire not only scientists, but artists as well. Okay, and here are a few examples. And they involve dark matter, they involve stars, and they involve gas. Who should merge? That's a very important question. If we defined, I mean, we do oversimplification. We define galaxy as being spherical, non-rotating, and all the galaxies are identical, have the same mass. Now I want to define the energy per unit mass. I want to define the specific angular momentum. I didn't have time to change so we will use BINI and Tremaine letters. And so what you have here is the diagram of specific angular momentum versus energy per unit mass. It immediately outlines a forbidden region, which is bordered by the circular orbits. So galaxies cannot move here. I mean, at least merging galaxies. Anything to the left of this vertical line, which has energy, binding energy 0, will be on elliptical orbits, and these guys will merge very efficiently and quickly. However, galaxies that are not on elliptic or not on bound orbits, but on hyperbolic orbits, also have a chance to merge, and that is because the galactic interactions are sticky, because the galaxies have internal degrees of freedom which can be excited. So what I want to highlight is the mergers are possible from unbound orbits also, not only from bound orbits. Typically, galaxies merge when the relative velocity, approaching velocity of these galaxies, is of the order of their internal dispersion velocity. That immediately singles out the clusters where the dispersion velocities are hundreds up to 1,000 kilometers per second, while the internal velocities are only 200-300 kilometers per second. So mergers will be inefficient there. And in the merging process, the orbital angular momentum normally is expected to be absorbed into the spin of the remnant. What is clearly very important in merging process, and that makes them sticky, it's dynamical friction and tidal interactions. Classification, a little bit of zoology. Binary mergers. Two galaxies are involved, okay, and one can define major mergers as the ones that the mass ratios are between 1 and 1/3. Minor mergers are everything else. Multiple mergers, or cannibalism, as it is usually called on the street, when more than two galaxies are involved. Okay? And then I would like to distinguish and maybe even get to discuss them, and that is mergers in gas-rich systems where dissipation is dominant, and we call them wet mergers, and in gas-pool system when we call them dry mergers. So what is important, I mentioned a minute ago, in merging process, which makes it more efficient, is dynamical friction. In dynamical friction, you have a massive guy moving within the field of less massive guys, and the acceleration or deceleration is given by Chandrasekhar formula, where most important is the density of the background, the velocity of the intruder, and its mass. So basically what happens is the dynamical friction force depends on the mass squared of the intruder. So dark matter, by the way, is the one that contributes dramatically to dynamical friction. I only want to show one case, I don't have time, of some old movie by Chris Michos, and you see here that the satellite quickly finds its way to the center. Here is an important point, which I accidentally found this paper. I was not aware of it before, and that is where you have, this is, of course, observations, galaxies in, galaxies in 5 massive galaxies in the cluster around redshift 0.6. On the right, you have numerical simulations with dynamical friction, the top 2, from redshift 0.6 to redshift 0, and without dynamical friction. And you see, without dynamical friction, they don't merge, basically, even in 6 gigayears. Well, physical processes during the merging. Dynamical friction, I already mentioned. No. Phase mixing and violent relaxation. The two-body relaxation is completely inefficient, as already known as Zwicky paradox. Phase mixing. This is the simplest. This is what you do every day when you drink tea or coffee and you try to mix the sugar or whatever you put inside your drink. And basically, what I would like to show you is that if you defined for, say, stellar system, collisionless system, you define the distribution function in the configuration and the velocity space, so in the phase space, basically. The convective derivative should be 0, comoving derivative of this function, simply because of the Liouville theorem. However, as was found by Lyndon Bell in 1967, an incredibly influential and intellectual paper, is that if we, instead of defining the so-called fine-grained distribution function, instead of this, use the finite resolution of our eyes, okay, and that means that we average over small details. So that would be the coarse-grained distribution function. Here it is. This is actually the fine-grained distribution function, but we can convert it into the coarse-grained. So we start in the R phi, which is the azimuthal angle. We start with initial conditions, and we mix them, like in the cup of tea, and you see what happens with the function. It evolves constantly, but if you use a finite resolution of your eyes, at some point, you don't see anymore this the fine-grained distribution function, and that is basically written here, the corollary, that the phase mixing is destroying the structures or substructures, whatever you call them, in the phase space. Violent relaxation. Well, in the violent relaxation, what is important to remember only one thing, that a system can be time-dependent. And that means the change of the energy will depend on the time change of the potential. As a result, the energy is not conserved. It can change with time and lead to relaxation. And the finite relaxation is very interesting when the particle velocity field is independent of the particle mass, which means the temperature of this collisionless fluid would be proportional to the mass of the particles. Yesterday, Jacqueline said that she doesn't believe in the dry mergers. So here's the example of dry mergers, which we are going to discuss as contrary to the wet mergers, if I will have time. Merging of two elliptical galaxies, so stars and dark matter only, in these four representative pictures. And here on the right, this is like C pairs out of a number of pairs that have been found by GEMS collaboration. There are the details here of these guys. Not many, but nevertheless, they look like some of them are disks, apparently without cold gas component, and some of them look like ellipticals, but the important point is that numerical simulations in this case predict that merging of such systems will lead to spheroids. End product. One more point about the dry mergers, which is of interest, and that I just picked up two scaling relationships. One Faber-Jackson, and the other one Kormendy, which are described here. And here are the figures with theoretical lines and numerical simulations, and you see that both scaling relationships are violated by the dry mergers. So that is interesting. Wet mergers. What is important in wet mergers is, of course, the energy, the orbital angular momentum, the galaxy spin, and the orientation between spin and orbital momentum, the galaxy inclination of the galactic plane to the orbital plane, and whether they are prograde or retrograde. And prograde, let me tell you a small secret, are more successive in merging. The first time, this was tested in 1941 by Holmberg in two-dimensional simulations, where he used the then available supercomputer made out of 74 electrical bulbs. And he thanked the Edison bulb company for donating this to science. So there have been scientific results out of this simulation. In fact, he was using this idea that the intensity of light goes as 1 over r square, exactly as the gravity, and was running from bulb to bulb, measuring the intensity of light. The scientific result was that he wrote it in his paper, that when galaxies interact tidally, this will generate spiral arms. I made a list, which I'm not going to go over, of what are the all the possible environmentally dependent evolutionary process that I'm supposed to discuss, but I will not do this, and also other additional effects of wet mergers. But I would like to emphasize something that was done for the first time maybe 20 years ago by Francois Schweitzer and really got my attention. This is the Hubble diagram, right? Does it tell us something? Okay, but there are caveats, as I wrote. Well, I don't have time to go over all the details of disk mergers. And the first thing I wanted to do is to talk about pure stellar disk without the wetting component. And the answer is that these mergers lead to spheroids. So the main point here is that there is success. And so maybe some of the ellipticals form as a result of these mergers. But then there are clear failures, because in the phase space, these mergers cannot reproduce the elliptical galaxies, which are much more centrally concentrated. And there is a clear need to include the dissipative component. Okay. This is basically what I just mentioned as a problem. There are other things that these mergers can teach us, and in fact, the tidal features that appear even when we have only dry stellar disks are quite sensitive to the mass distribution and the total mass of the halo, as you can see from this nice work by John Dubinsky a few years ago regarding the tidal features. However, the most interesting point is, of course, when we have the wetting component. And the SEN-A beautifully shows us that the universe is much more diverse than we've been thinking. What happens if we have dissipative components? Well, here is the example of Milky Way type galaxies with 10% gas and merge. What we have here on the left, this is the stellar component, and then if you zoom in about factor of 20, you see the stellar component. Unfortunately, it's black and white because it was done in the mid-90s. Okay, but clearly it shows that the gas is much less tolerant to the merger and falls to the center. There are interesting points here, and that is about the surface brightness of the resulting galaxy, which in many cases, in some cases, let's put it, resembles the Vauquelin profile. So one can say that when we have these mergers, including gas, we can form ellipticals, some of them. The $100 question is, it doesn't leave an answer what fraction. There are problems, however, for example, with missing metals. Here you have, the problem is, of course, that the typical ellipticals are more metal-rich than if you assume that they come as a result of the two disk mergers. Here is the mass in metals, typical disk merger, without bulge, with bulge, and these are the typical present-day ellipticals. So you see, there is a problem. There are ways out, and maybe the universe is more complex than we think, but that also makes it less beautiful, maybe, for us. So there is no problem that I want to mention when you have merging resulting ellipticals made out of disks. And that is in binary mergers, there is not isotropic. The velocity distribution is not isotropic in the collisionless component, while the ellipticals, the massive ellipticals at least, are. Oh, it tells us something. Well, maybe I will try to be explicit, simply. The gas-rich mergers, not just wet mergers, but the gas-rich mergers. And the $100 question, and after addressing this, I will finish. Do they destroy the galactic disks, or make them thicker? There are two opposing views on this, and I listed the most known names in the left category. However, these early mergers and early claims been talking about models without gas. So this group claims that disks must grow rather quiescently. As you understand, of course, if one claims A, somebody will claim B. And that is, what about the leftovers? Now, we don't care about collisionless leftovers. What about the gaseous leftovers? And here we have simulations with gas. And the answer is that there are plenty of leftovers if the disks are gas-rich. The $100 question, I already probably went to $1,000 in my $100 questions, is what is the critical fraction of the gas in order not to destroy or just thicken the disk? Well, this is the simulation by Sprinkle and Herpes 2 years ago, where they assumed the extreme. They assumed that the disks are just gaseous disks sitting inside dark matter halos, and they're on prograde parabolic orbits, so everything works for the merger, and you see the result of this merger. On the left, these are stars, because there was star formation in these gaseous disks, and on the right, there was a gaseous component. So this is at least proof that if we are lucky, if the galaxies are lucky, then disks can reform after some major mergers. Can you wait for 3 minutes? Yeah. If I will finish in 3 minutes. Okay. So disks can reform after mergers, and here is an interesting simulation from Governator, 2 years old, which had a merger at around redshift 0.8, and the merger was completed by redshift 0.6. Then the disk was quiescently growing with quite a lot of cold gas accretion. And here is the redshift 0 in the simulated I-band. And the bulge-to-disk ratio after the merger was 1:1, which is rather uncomfortable. But by the redshift 0, it went down to below 0.5. Here is the final product of this simulation. And what you see at the top, this is so-called thin stellar disk. and here is the thick stellar disk. The beautiful thing that happened here is that although most of the mass is in the thick disk, most of the light is in the thin disk, and so the thick disk simply faded from the time of the merger to redshift 0. Okay, but then there is this another $100 question: is, well, all these things, tricks of fine-tuning work usually if you invest a few months in them. But then how much fine-tuning the nature is capable of tolerating? What if you go and use other initial conditions? You need to fine-tune it differently. This is what nature tells us. We have galaxies with thin disks and thick disks. I mean, this is the same object. And the idea is maybe the extent, the radial extent of the thick disk tells us whether this thickening was abrupt or adiabatic process. Okay? And the problem is that uncomfortably large fraction of galaxies have no thick disk whatsoever. I will skip this. And the only thing I want to say is that when we go to high redshift, and we have this, well, here, particularly redshift 2, we have the so-called or so-called claimed disks, or protodisks, which are very gas-rich, which are very massive. They form stars like crazy, 140 solar masses per year. The ratio of the gas to the stellar mass is half, and in less than 300 million years, they should take away all the gas. There are no obvious signs for merger, at least claimed by Genzel et al. 2006 paper. He doesn't see any velocity anisotropies, I mean asymmetries, sorry, not anisotropies. And so this object was concluded as it is not obvious merger. Then came the numericists and used all this beautiful visualization technique and actually been able to reproduce the same object in merging. And so they claim that this is consistent with merging. So I probably should stop here.
Could you go back maybe about 15 slides? You show this simulation by Mijos and Hernquist that produced the dense central component in a merger remnant elliptical. And while he's looking for it, I'll say, this is a meeting on secular evolution,
This?
which is...
No,
it was...
What was it about?
There was a simulation by Mijos and Hernquist which produced an elliptical galaxy that had an extra central component. And you remarked on it briefly, but you didn't say very much. Now, I don't remember exactly where wait a minute, don't move. That's it. Down
this?
One down.
One down?
That one.
This?
Yeah,
Yeah.
Thank you. So, this is a meeting on secular evolution, so I didn't come prepared with a talk on elliptical galaxies, which are not made by secular processes, but fast ones. But we're hearing a lot about these things, and it's worth making this one really cries out for a comment. And it's in the context of your comment that you don't quite feel sure that mergers can make the properties of all ellipticals. And I think the story is now much more optimistic than that. The answer is really looks very strongly to be that the details of what we see in ellipticals we really can understand, and they're all understandable as one aspect or another of what happens in the context of mergers. And this is a good example of a surprise that turns out to be understandable. The bottom right panel shows the density distribution of the remnant, that one, of a merger that contained both, in which the progenitors contained gas. And what happened is that in the merger, there's violent relaxation, And the violent relaxation takes the stellar distribution that was there before and turns it into the outer and shallower part of that profile, which is just slightly curved downward. The gas that was in the progenitors does what it always does in mergers. It falls to the center, makes a very high-density central component. They had a Schmidt-Kennicott type star formation law in there, and so it turned into stars. And the very steep profile that you see there that extends above the outer shallow one near the middle is the starburst remnant. You can see the word starburst at the bottom there. So that steep thing was the thing that was made during the merger out of the infalling gas that naturally happens in a merger. And they looked at that result and said, oh, gee, we're embarrassed, because elliptical galaxies don't look like that, do they? I spent about a half a page being embarrassed. And this paper was written in 1994 when nobody knew that ellipticals looked that way. But in a recent paper that I wrote with a collection of colleagues in 2009 AppJ Supplements, we followed up on actually something that I found in 1999, which is that when you look at the lower luminosity ellipticals, the guys that don't have cores, don't have missing light at the center, they don't have featureless profiles into the middle. They have an extra component that looks exactly like that. And in fact, we found that extra component in all of the galaxies that didn't have cores. They either had cores or they had extra light. They didn't ever have a de Vaucouleurs law. And we interpreted that as a result of wet merging doing exactly this, having a starburst in the middle. And also wrote a couple of papers with the Hopkins group where they modeled the process that I'm now talking about and produced also objects like that. So this kind of thing, which at one time
Hopkins
in 1994...
anything you want.
Dissipation in gas that's in a merger is not particularly negotiable, if you ask those folks. Exactly what they predicted we now see, and this particular little piece of mystery is gone. We understand it now, I think, and that's what merger remnants look like when they're wet mergers.
Okay, I would like to hear something from students.
Yes, please. Please. So, you show a simulation, nice simulation with a lot of gas inside, a few slides before. And in this simulation, you said that at the end we have a galaxy remnant with a lot of gas and which reform a disk, right? But on your intensity distribution, I cannot see any star clusters, for example, globular star clusters. So can you trust a simulation with a lot of gas which do not form star clusters during the mergers?
Well,
because this is observed as well.
Think about this as being a distant galaxy where you don't have enough resolution. I could zoom in, assure you there are star clusters there, because there is star formation there.
Right, but I cannot see.
Well, I mean, that's because what is shown here, and the other is the unresolved picture, I mean the low resolution. Mm-hmm. You need to zoom in order to see the star clusters. I assure you that there are star clusters there.
But because the mass unit is important.
It has other problems, but star clusters are there.
Can we see the plot that you showed in the beginning again, with radius against angular momentum?
Radius against angular momentum.
A bit down, I guess.
Radius against angular momentum.
Yeah, it's. I can ask it based on this question.
This?
Yeah. So I was looking at this, and you said that the top line was what the models proposed, and the bottom line was what you...
You're talking about the right?
The left panel, sorry.
Oh, the left, yeah.
So I was just looking at this, and one thing I noticed is that it seems to me that it doesn't go through the zero, if you just be honest with fitting a line.
You mean the point distribution?
Yeah, the point distribution. It's really weird. For my eye.
Well, that may be some stupid selection effect. Observers always full of this. don't take it too seriously.
All right. No, that's. I just thought that this is a weird plot, but.
Well, I mean, I would say that there are almost no objects below 100 kilometers per second here. You don't know how they behave. What you see here is for more massive guys, right?
All right.
This is Corto's sample from 1997 of local galaxies.
Yep. Hi. Yep. Yeah.
Well, then yell the question. Shoot.
Yeah, if I understood right, you are supposing that your mergers doesn't have your galaxies that are merging doesn't have rotation. They are not rotating.
Oh, they have.
They have.
Yes, I mean the dark matter and baryons acquire the spin as they expand in expanding universe before the shells turn around and go down. So yes, they have, and the average spin is around something between 0.03 to 0.05. So they do.
Yeah, but you said
otherwise they would not form disks.
But you said in one of the slides, if I remember right, that you are assuming a very simplistic model in which you are assuming that your mergers doesn't have your disks are not rotating. Or maybe.
Oh, that's not me. That's James SPINY and Scott Tremaine. But I assure you that their intentions have been completely noble, and this is not important. What they wanted to see is if you take two spherical galaxies, can we predict whether they merge and not? And that's all. So, yeah.
Okay.
We don't want to bring all the complexity of nature solving these simple problems, right? Yeah.
Yes, I have a question about the number here, at the side of the, of the other question, about the number of mergers that you must have to form a disk. Because some persons say that you need a lot of mass or a lot of dark matter halos to end with a galaxy, with the baryons to follow and form a disk.
That is a very interesting question. I can assure you that there is more than one way that the nature allows us to form a disk. Because there is the universal ratio between baryons and dark matter, okay? And apparently the galaxies are not more than by a factor of 2-3 away from this universal ratio. In order to have a disk of particular size, you also need to have a halo of a particular size. So how it is acquired, how does it happen? It depends where the halo was born. Is it in the field or it is in the cluster? And some of them will, in particular environment, will not even reach this type of maturity. But if you ask me whether these are minor mergers or major, can we do it in one run? Both are possible. You can form a disk with one merger, and you can form it very slowly with minor mergers or even without mergers. So, if this is what you've been asking? Yeah.
Here. Isaac, I've got some good news on thick disks for you, because we've been looking at adjoint galaxies in the S4G survey. And
then there will be bad news after this?
No, we haven't found any that do not have a thick disk. They all have thick disks, including this one you showed, NGC 4244.
Has a thick disk?
It has a thick disk. It's feeble, but it's there. And we wrote a paper on it, Comeron et al., FJ 2011, earlier this year. So even your counterexample does have a thick disk.
Oh, that's good. But you will need to find a few other thick disks. One case is not enough yet.
No, all the others have thick disks. This one has a very feeble one.
You don't find any objects without thick disks?
Exactly, they all have a thick disk.
Oh, okay. Okay, that makes sense. You know, there is a very old, I already told this to somebody this in this meeting. You know who's Landau? yes, Landau Lifshitz. So he was known, he was a very outspoken scientist. He was going in the corridor, and two experimentalists been trying to digest a particular experimental curve. Without asking, he took the paper from them and started to explain them what this curve means. And it was difficult to, unpolite to interrupt him, and after 15 minutes he finished, and they said, but Professor Landau, it's upside down. He looked at this, he said, this is even simpler to explain. So,
yes. I have a question.
Oh, you? Then ask.
So after the presentation, it seems that it is still controversial how much merging can explain the evolution of galaxies in terms of metallicity, sizes, and profile, etc. So in your opinion, what is it that we need to know to infer and have an answer to how important mergers is? Is it the limitation in theory or computational power or observations?
It's all together. I mean, my point is that if I would know the ultimate answer to this, I would, instead of coming to this conference, would sitting and writing the paper. But the problem is that there's possibly, more than one way to answer these questions. You can arrive at the present state of the universe maybe more than one way. What we're trying is not only to explain the current state, but also to find out which way it got there. It's quite difficult. But there are problems around. In the smaller problems, which may pop up later as big ones, I didn't even mention. But there are problems with numerical simulations. There are problems with our knowledge of basic physics, classical physics. We still don't know how to treat viscosity. And all this stuff that I will be talking on Thursday, for example, cold accretion rates, all the viscosity, accretion disk, everything. So we don't know this. At least we are aware that we don't know. Renil.
I have the feeling that these merging models take a very strong piece of information, a very strong constraint, the color magnitude relation or the color mass relation, not really that much into account, because this relation is very tight. If you have dry mergers, you go off. You showed a few things that indeed things are violating. Things are violating. So dry mergers by themselves. Personally, I have never seen them. I've seen one. The moment you see one, you go in detail, you don't see the dry merger anymore because you start seeing dust and whatever. Have you ever seen, you mentioned the word dry disk. This is a ridiculous word because I've never seen any dry disk that exists. Even the people that classify disk, Xander, whatever they classify it as an S0, you look in detail, there's things there. So there's always interstellar matter. Just look at it the other side. Stars lose a lot of mass all the time. So galaxies must produce in their lifetime enormous amounts of gas. That gas must go somewhere. And usually it goes in forming stars or forming dust or whatever. So all that stuff creates always things like things like star formation, and how it goes and how this is provoked, whatever. I mean, that's a different story. So,
well, I will not defend the existence of dry mergers because I learned on my own experience that you cannot say absolutely no in astrophysics. There is always at least one example in this universe that doesn't follow even the Newton's law. So my answer is maybe this is a small number of objects. Maybe they are not really important in our overall understanding of galaxy evolution. However, the original idea was that you naturally form ellipticals out of this. Now it is clearly questionable, but we cannot say that there are no dry mergers, and I showed you some examples. where people claim.
Well, I mean, if you show that picture again, I mean, do you really want to call these things dry? Well,
it's Eric Bell.
Those galaxies were at high redshift. You don't know whether there was gas or not in that example. So that's their news point.
No, there is isn't. We can go into details if you want, but my understanding there was a claim in this paper that there is no substantial gas component, cold component.
How do they know?
I forgot what was but we can take a look at the paper. And more than this, they claim that they looked on the colors, and they claimed that there was no recent star formation
So
there.
that was the point that I made yesterday.
Yes.
That I selected nearby galaxies, merger remnants, based on that color criteria.
Mm-hmm.
These galaxies have gas masses from a few times 10 to the 8 to a few times 10 to the 10. They are some of the most gas-rich systems. At higher redshift, you don't know how much cold gas there is.
I absolutely agree with you. I don't want to defend Eric Bell's paper, but there are other claims. Van Dokkum, for example.
This is what we argued that was wrong.
He was wrong.
He is wrong.
Interesting.
So I agree with Vernier. It is not that there is one system that's different. I don't know of an example of a dry merger.
Well, that doesn't mean that they don't exist. But I will tell you, we really don't need them. So the question is beyond this.
What sort of confuses me in your story is, or the story of some of these people, you need very gas-rich galaxies to form ellipticals. Those are very gas-rich disks. You need very gas-rich disks to form disks. So where do we start?
But what do you do with the galaxies that have very little cold gas? Suppose, the galaxies appear to be doomed in the sense that they all will fall within the same potential wells. And so, I don't know, in the future, the M87 will merge with some other giant elliptical galaxy. What do you say about this merger? The M87 doesn't have a dynamically important cold gas component. So with a little imagination, it may happen, but it may be not crucial for evolution.
Ellipticals around M87 have relative velocities of a few thousand kilometers per second, so they are very unlikely to merge. That's the point. In the centers of clusters, there are ellipticals that have no gas.
It's a matter of time only. Of course, it's dynamical friction.
Okay. Yeah, and a few.
I said, if you just sit and wait around. Talk to me, Leah.
It depends very much. Okay, I have some simulations of that, and it depends very much on what part of the gas does in the very what part of the gas goes to the center to start with. Now, whatever was stars to start with will make something which is spheroidal. That's a bulge or whatever you want to call it. The other stuff, the gas, part of it goes to the center and makes stars, but most of it, or a very high fraction of it, exactly. And that, little by little, starts falling in afterwards. But take a time, And when it falls in, it starts, because it's got angular momentum, it's out there, a little bit of velocity out there makes a lot of angular momentum. So when that gas will fall, it will form a disk. And that disk can be beautiful. I've got some disks which are really, some exponential disks, which are really fantastic. And they're formed just in the way Isaac doesn't like. Sorry. And yeah. Okay. Right. Yes, that's right.
Okay. Since the three of you still have some lessons, shall we go for a coffee?